Random access memory. So we're going to talk about RAM. This is our volatile storage. So with RAM, once you turn off the computer, you lose that information. So what is it? It is the workspace for your computer to process data. So the way I like to think about RAM, and I was always explaining to my customers, is I tell them it's like their desk. If they have a bigger desk, they can have more stuff on their desk at once. If you have a tiny little desk like on an airplane, you can't get much work done, right? Because you have a very small amount of air you can pull out at a time. And so if you want to do a lot of things at once, you better have a big desk, right? Or like, my wife, she always complains that the kitchen's too small. We need a bigger kitchen so she can do more at the same time. She needs more RAM, more desk space, right? RAM contents can be changed at any time by the computer because they're constantly being able to be changed. The RAM, when you turn off the power, all the data inside is lost. It is used for your programs, your data, and your disk caching. Because we talked about hard drives are very slow, RAM is much faster. So what we'll do is we'll actually take stuff from the hard drive and preload it into memory, into RAM, so that when the processor needs it, it can grab it quicker. Again, it's kind of like the RAM might be where Sarah's sitting in the back, and the hard drive might be down in the parking lot, right? And so if I need to go to the hard drive every time I want to get something from my car, it doesn't be waiting a while. If I just have to go to Sarah, it doesn't take me as long. So maybe I'll have Nick run to my car, get it to Sarah, and keep running back and forth and bring things up. So I can just go to Sarah and get it. That's kind of the idea with RAM, right? More RAM is going to increase your transfers between the CPU and speed up operations. Because if you don't have enough RAM, what Windows does, it makes virtual RAM by making a file on your hard disk called a swap file or temporary file. Or page, in Windows we call it a page file, in Linux we call it a swap file. And so we can pretend we have more RAM, but again, it's going to a hard drive, which is a very slow device, so it's going to slow down the machine. So if you have a computer that's constantly accessing the hard drive and is really slow, best thing to do, add more RAM. It'll solve that problem. So RAM, it does disk caching, like I was just saying, right? We use RAM to hold recently accessed disk sectors. We can use virtual memory, which is a slow substitute for RAM. It's a file on your hard disk that will emulate these physical RAM chips. So if you don't have enough RAM, say you only have a 4 gig in your machine, but you need 8 gigs to run this program, what it'll do is it'll put the other 4 gigs on the hard drive and constantly be accessing the hard drive, which means the whole program's going to slow down. RAM is faster than magnetic or optical storage. When I talk about magnetic storage, we're talking about hard disks. We talk about optical storage, we're talking about CD and DVDs, right? Because they use laser to read those, they're optical. RAM is very fast. It operates in what's called nanoseconds, which are 1/billionth of a second is a nanosecond. That's pretty darn fast. I talk fast, but not that fast. Magnetic media is relatively slow. It operates in milliseconds, which is thousandths of a second. So we're off by a big factor here between thousands and billions, right? So RAM, we have memory modules are different types. They're defined by the motherboard based on that chipset. So if I buy this motherboard, it uses a DDR2 stick of memory. If I use this motherboard, it uses DDR3 memory, right? That's going to control which will physically fit on the motherboard. The memory chip type, older systems use different chip types than our newer systems. Our newer systems are using DDR3 systems and above. Your memory modules, we had 3 different ways of measuring speeds in RAM. We started out in the old days in measuring it based on nanoseconds. So we said, hey, this is 60 nanosecond RAM, right? But what happened was they kept getting memory faster and faster, and there wasn't enough nanoseconds because you start getting down into the 1s and 2s and 3 nanoseconds, right? Makes it hard to define which one is which. So then I said, okay, let's do it based on bus speed. And so I started doing it based on PC dash and then its number. So PC dash 133 is 133 megahertz. That's 133 millions of times per second is how fast it's operating. And then we had throughput, which is the newest way of doing it, where we write PC2 6400, which tells me that it's 6400 megabits per second or 6.4 gigabits per second is how fast and how much throughput we can actually send through that data. So when you look at new memory, for instance, if you go to the store, you might see something that says this is PC3-18000, which means that it is DDR3 RAM, because it's PC3 is DDR3. And then if it's 18,000, it is 18 gigabits per second. Pretty fast stuff, right? And so we keep getting faster and faster all the time. So RAM, we have the allowable module size and combination. So some motherboards require the same speed and type. So if you noticed on our motherboards, we had 4 RAM slots. We had 2 sticks in there right now. Some motherboards have what we call banks of 1, where you can put a single stick in. Some you had to do in pairs called, you had to do them in pairs to do a two to a bank. Ours actually will support one at a time. Okay. Older systems, you had to do it in pairs. Newer systems, they'll do one at a time. Again, you have to check your motherboard to figure out what it supports. So the total number of modules to install is going to be limited based on how many sockets are on the motherboard. These particular systems have 4 slots. If you go to some servers, they have 8, 16, 32 slots, right? Because you need a lot of memory for those type of systems. If you have a smaller footprint, it's going to have less area to put memory in. My laptop has room to put 2 sticks of memory, right? If you get one of those small little mini desktop or mini computers for your computer system, it may have 1 or 2 slots in there. If you have a big tower, like you had a big old tower at home, you could probably put 8 or 10 sticks in there, right? It just depends on how many slots there's going to be. So we have all sorts of different kinds of memory. We're going to start out with the old stuff, and then we're going to move to the new stuff. This particular slide is not covered on the newer 901 exam. It is covered on the 801 exam. You just usually don't see a lot of questions on it because, again, this is really old. DRAM is dynamic RAM. It was a constant refreshing of the contents, and it's obsolete because it's been replaced by newer types. Essentially, all of our RAM we have nowadays is based off DRAM, okay? And what it did was, let's say I gave you guys a phone number to remember, right? Have you ever done that? Like somebody gives you a phone number, you didn't have somebody to write it down with. What do? You should then keep repeating it to yourself over and over so you don't forget, right? 567, what is it? 867-5309, 867-5309, 867-5309, right? Keep saying it until you can write it down. That's what DRAM does. If it didn't keep refreshing it, it would lose the memory, okay? Static RAM, on the other hand, didn't require this refresh it. Because it didn't require refreshing, it takes less processing power. It's used in the CPU cache. So when we talked about level 1, level 2, level 3 caches, that's what we use static RAM for. But it's very expensive, very fast, very good, but very expensive. So it's only used in small quantities. Synchronous RAM was the first memory to operate at bus speed. So before you had the motherboard operating at one speed, the RAM operating at another, and the CPU operating at another. With SRAM, we started syncing those up to operate at the same speed. Because if we're all marching to the same drummer, we can do things more efficiently. These were 168-pin modules rated in megahertz. It's PC66, PC133, PC266. This was the first DDR or DDR1 essentially. We now use, again, this is an evolution of dynamic RAM. And both of these evolved into DDR2 and DDR3, which is what we currently use. So we have DDR. Double data rate is what DDR stands for, and it is an SDRAM. It is a synchronous dynamic RAM. It performs 2 transfers per clock cycle. So because our processors were getting so fast and our bus speeds couldn't keep up, they started doing double clock cycles. So I did 2 transfers, and then we hit the next clock cycle. And again, this is, PC 1600, for example, right? Its DDR is 1. So if you see PC with no number, it's DDR1. If you get to DDR2, it was double data rate, which was basically the next evolution. And what it did was it ended up getting it could do faster external bus speeds. And so it had higher speeds. So when we talk about PC2, we're talking about DDR2. And again, that 4200, 3200 number, that's how many megabits per second it can transfer. So 4 gigs, 3 gigs, etc., right? We get to DDR3, our speeds went up higher again, right? And you see that with the PC3, that's DDR3. 8500, that's 8.5 megabits or gigabits per second, right? Or 8500 megabits per second. 10,600 megabits per second, right? 18,000 megabits per second. We have really fast memory now. Most of your machines at home are operating in this PC3 10,600 or higher speeds. Okay, someplace in the 10 to 20,000s is generally what most people are using now. Some are routine 10 and 20. So another type that was out there that was not used very often and is no longer covered on the new exam is what's called RAM bus. And RAM bus, or RDRAM, is also known as RIM, for RAM bus inline memory module. It had 16-bit and a 32-bit version. The big thing you need to know about RAM bus is it wasn't used very often. And it had this thing called a CRIM, a continuity module in empty slots. So in our PCs over here, we have 4 slots, right? If we were using a RAM bus module and we only put 2 in, we would have to put these 2 CRIMs in, which are blanks, essentially, blank circuit boards, to give that continuity. Every every slot on the motherboard had to be filled with it. So if you're not using it with RAM, you had to use a blank. So that's what a crim is. That's the only thing you really need to remember about the RAM bus modules. Like I said, they're not very heavily used. They're relatively slow speed. I mean, you're seeing here 4,200, but we're talking speeds of 10 to 15,000, right? So very slow. Usually used in server environments, old Intel Pentium 4s. So you can see how old we're talking here. And again, it's not covered by the new exam. So a lot of the old exam questions have been taken out because of that, as they're morphing towards the new stuff. So here's some other examples of older technologies as well. SIM was the single inline memory module. SIP is your single inline pin package. So RAM bus is your small outline RAM bus module, which is a laptop version of RAM bus. Again, if you thought RAM bus wasn't used much, the laptop version of RAM bus was used almost none. DIMM dual inline memory module, again, a very old style. And SODIMM. SODIMM we'll actually talk about again when we get to laptops. SODIMM is what you use in a laptop. Small outline dual inline memory module. And they come in DDR2 and DDR3 varieties. They're called SODIMM DDR2, SODIMM DDR3. But those are useful, so we will remember it. On this slide, that's the one to remember. It's SODIMM. So, your memory module width. So when you look at your RAM, it's classified by how big the width is in bits. So it can be an 8-bit, a 16-bit, or a 32-bit variety. But now everything is being done as 64 bits because we're using 64-bit processing, right? So we want 64-bit RAM. That means on every clock cycle we can send 64 bits of data, which makes sense since we're a processor that accepts 64 bits, right? Memory must be added to the banks to ensure the width equals the width of the memory bus. So if you have a 64-bit bus, you need a 64-bit chip, or you need two 32s to make 64. Depending on how your motherboard is set up. The other thing you can do is what's called dual and triple channel memory, okay? So you can do things in single, dual, or triple. If you do dual, it's twice times 64. Triple is 3 times 64, right? We'll talk about that more here. So a single channel, it's our normal method of accessing it. So if it's 64 bits, I'm going to send you 64 bits at a time, okay? If I do dual channel, which is how we have ours set up here, we have 2 memory sticks working in tandem. So they are both identical in speed and size, and they can work at the same time. And what it does an interleaving of memory access. So when it's accessing the memory, it gets part off of this chip and part off of this chip, so it can do it faster. It's like if I had 2 instructors up here and you ask a question, he takes half the question, I take half the question, we can get your answer to you twice as fast. That's the idea behind it. With triple channel, we have 3 modules working together, and they're interleaving that memory. So when you're using dual, it's twice as fast. Triple channel, 3 times as fast, right? That's the idea of it, is that we're interleaving and going faster. It's like 1 horse can pull 100 pounds, 2 horses can pull 200 pounds because they're working together as a team, right? That's the idea behind it. The other thing we look at with memory is parity versus non-parity. And I know this sounds kind of funny, but non-parity is a memory that doesn't check for errors. It's your standard everyday memory. So it does its best it can, and it just does what it can, and if it does well, great. If it has a mistake, that happens too. This is a standard memory that we use for our workstations, our computers, and our laptops. Parity, on the other hand, as a way of checking for errors. So the way it works, and this is kind of an eye chart, you don't have to fully understand the way this works, but if you look at the top line, the original data was all zeros. If we're using an even parity, it's going to look and say, if everything is 0 and my parity is 0, that meant that these were all zeros, and that's correct, because if I add up all the zeros, that would be 0, right? With the next one, you can count how many ones there are. 1, 2, 3, 4, 5. If there's 5 ones, that's an odd number. So therefore, it's not even, so we get a 1 there for our even parity. And all it does is, if I was sending you this series of 1s and 0s, and I transposed one of them, that parity, that check bit, would identify the fact that there's an error, right? You wouldn't know what the error was, but you'd know there was a problem. It's kind of like double checking your math. If the memory module requires 8 chips for data, then there's going to be a 9th chip that's set aside for that parity. The other thing we can do is what's called error correcting code. I'll talk about that in a second here. That's what ECC stands for. The parity relies on checksum calculation. So as it goes through, every time it gets data, it has to do a calculation. Go, let me count up. How many 1s was there? There's 5. That's an odd number. Therefore, I expect a 1 there. And if it got that 1, it says, okay, that's good, move on. But if it didn't, it go, up, there's a problem. And if you're using parity memory and there's an error, its response is to shut down the computer when there's a problem. So instead of just working through it, just oops, I don't know what to do, and crashes. So that's not very good, and your data gets lost. Error correcting code, on the other hand, is going to take it a step further and do the parity stuff, but when it finds an error, it's going to try to correct that error. That's why it's called error correcting code. And so what happens is it's used for reliability of memory. It's slower though, because all these calculations take time. And so it's slower than non-parity and parity, but it does add reliability. So for servers and workstations that need to be highly reliable, this is a good thing to use. If you have like a router in a network that needs to be highly reliable, they'll usually use this type of stuff. Same thing with servers. And if you count the modules here, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 because that ninth one is used for the parity and the ECC. Okay? That's that check bit that we were talking about. The other thing we have is we have single-sided and double-sided memory. So single-sided is like double-sided is taking like 2 memory chips and putting them on 1 chip. So you can get more memory on a single module. Okay? The module has memory chips on both sides if it's double-sided. And again, you have to make sure your motherboard actually supports it. There's not a whole lot of single-sided, double-sided conversation. Usually when you buy a motherboard, it'll say, go buy DDR3 16,000 speed, and you'll go to the store and buy that, and that'll work. So you don't have to worry too much about that. Buffered versus unbuffered. So buffered is also known as what's called registered memory. It uses a register that stores and buffers the data being sent from the memory to the CPU. It's used in systems that require high reliability, like servers with a large amount of memory modules. It reduces the electrical load used by these systems because it's buffering the data instead of having to constantly have to re-access it. And you have unbuffered, that's what we normally use in our machines. It relies on the memory and the CPU to transfer the data between themselves. It doesn't have this buffering going on. And you can see this is an example of a 1U server. See how it's big and long? This actually is a dual processor one. You can see the double processors. Right here is 1 and 2 processors. You have your memory chips over here. You've got a riser card to make it fit inside this very short case. See all the stuff we talked about, it's all coming together, right? And this thing's got a ton of memory, because you could see here on the left I've got 4 modules, and over here I've got another 4 modules on this side, right? So start seeing a lot of the stuff come together. That's a server, not an amazing gaming machine. I wouldn't use a 1U thing for a gaming machine. I think it would overheat too much. Gaming is very processor intensive. Yeah. So how do you install this memory? The allowable module size and combination is going to be determined by your motherboard, like we said. Some motherboards require you have the same size and speed. Older ones had to be in pairs. Again, check your documentation. We talked about you have to do it in either single or pairs depending on your motherboard. And your motherboard is going to determine how many sockets you're going to have available. The way you install it is we install it in what's called sticks of RAM, okay, into the slots on the motherboard. So we call it, remember we talked about expansion slots for those expansion cards. For memory, we just call them memory slots, okay? What you're going to do is you're going to take it out of your ESD pouch, your anti-static bag. You're going to make sure your computer is turned off. You're going to make sure you have the proper ESD wrist strap on. You're going to unplug your power cord. You're going to hold the memory sticks by their sides. You never want to touch the gold contacts, okay? And what you're going to do, this is not a very good thing to do. See how he's touching the side of it? You should be touching it by the sides here and the top. But you'll grab from the sides, put it straight in, and push down on the top, and you'll feel it click in place. When you do, those little flags on the side, the little plastic slot flags will come up and grab on and hold it in place. And we'll do this during our lab. We'll take the memory out and put the memory in. So you want to line up the memory modules with the slot on the motherboard. Then notice in the center there is a little key in the center of it. Right there. And so as you're going to put it in, see how he's grabbing it from the sides, that's good. You're going to verify the locking tabs. These little plastics are open. You're going to push it straight down until the tabs swivel into position. Sometimes this takes a little force. People are afraid they're going to break their computer because it does sometimes take a little bit of pushing. And you're going to push straight down until it clicks. Never touch those gold connectors because the oils in your skin will actually degrade those connectors, and it'll cause the memory to have problems, okay? Also, if you touch the chips, you can cause ESC damage, so you don't want to do that, right? So, which of the following RAM types supports triple channel configuration? So, we have a couple of answers here. We have RAM bus, DDR, DDR3, and DDR2. I didn't cover this directly in the lecture, but what do you guys think if you had to take a guess? C, DDR3, right? Why? Because it's newest and triple channel is fastest, right? We know it's not RAM bus because that's almost never the answer. In fact, on tests, I don't think there's ever been an answer that the answer was RAM bus. Every question I've ever seen from the test or heard of on the test, RAM bus has been a distraction. So, DDR3 is the newest and fastest, and it does support triple channel configuration, as well as dual channel configuration. That's the basics of our memory.